Hello, everyone. Good to see you again. I hope all you are doing very well. In this video, I'm going to talk about a formal language for understanding data. It's causality. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. We have learned about variations necessary to identify an effect in analysis. In this lecture, I'm going to formalize what we've learned by using the potential outcome causal model. Are you ready? Then let's get started. Let me go back to the discussion of variations. We need proper variations of measurable actions in data to measure the effect of the action. To answer the question about whether to discount the shelf price or not, we need variations in price that cover the discounted and regular prices. Then, we can measure the effect of the price discount by observing how much sales is boosted from the baseline. To determine the level of ad spending, we need to have variations in the ad spending level that cover both more frequent and regular ad spots. Then, we can predict the effect of the additional ad spending on sales by observing how much sales increases with the more frequent ad spot. In other words, we can formally say that we need to infer the causal effect of the marketing action on sales from data. For example, for the pricing question, the inference of whether a price discount causes an increase in sales or not, and if yes, how much it increases the sales. This inference task requires two separate groups of observations. One is treatment group and the other is control group. Then, the proper variation of the price discount action implies for the treatment group of observations, a discounted price is offered, and for the control group, the discounted price is not offered. In addition, except the price, all other things should be the same between the groups, so-called ceteris paribus in Latin. Then, how to get the proper variation? Suppose that you have a god who can do anything in this universe, including time travel. The best way to get the proper variation is to open parallel worlds perfectly identical to each other and just offer discounted prices only for one of the worlds. By observing what happens to the sales in two worlds, you can exactly measure the impact of the price discount on sales. But it is impossible in reality. No one does have that power. Then, how about this? First, find two places different from each other, but expected to be crowded with people randomly from the population of the market we are investigating. Then, just offer the price discount for only one of the places and observe the difference in sales between two places. Because the people in both places come from the same population, the average response to a price level is the same across the places. Thus, by observing the average impact on sales in both places, we can exactly measure the causal effect of the price discount, where all the other confounding effects are cancelled out. This condition of experiment is called randomization, which was suggested first by Fisher, 1925. And the goal of this lecture is to formally describe this condition in math. Fortunately, two econometricians and their colleagues have developed a well-defined model for the condition. It is called Potential Outcomes Causal Model by Neyman and Rubin. Let's say there are only one treatment, and DI indicates whether this treatment is applied to individual I. If it is applied, then DI equals 1. If not, DI is 0. And let Y1I and Y0I denote the potential outcomes of the individual for the treated case and the not treated case, respectively. Those potential outcomes are not observable at the same time because only one of them is realized. And let Yi denote the observed outcome. Then the observed outcome is given by this function of the potential outcomes switching by the treatment assignment di. If di equals 1, the first term becomes y1i, and the second term becomes 0 because 1 minus di is 0. And if di equals 0, the first term becomes 0, and the second term becomes y0i because 1 minus the I is 1. This equation is called the switching equation, which picks one of two potential outcomes as the observed outcome in accordance with the treatment assignment, Ti. Before moving forward, let's make an assumption first, which is called stable unit treatment value assumption. This assumption implies the treatment received is the same across all individuals who are treated, and the treatment applied to an individual does not affect any other's outcome. That is, there are neither externality nor spillovers. Given the definition, the causal effect of the treatment on individual I is measured by the difference between the potential outcome for the treated case, Y1I, and that for the untreated case, Y0I, and let delta I denote the causal effect. Then, the average causal effect, so-called average treatment effect, ATE for short, is the mean of delta I. By the property of expectation, it is the same as the mean of Y1I minus the mean of Y0I. There are two more versions of the average treatment effect. One is the average treatment effect only for the treated, so-called ATT. This effect is given by the mean of delta I, conditional on the treated, and by the property of expectation, it is the same as the conditional mean of Y1I minus the conditional mean of Y0I. The other version is the average treatment effect only for the untreated, so-called ATU. And in the same manner, this effect is given by the mean of delta I, conditional on the untreated, and it is the same as the conditional mean of Y1I minus the conditional mean of Y0I. And here, only two of the components of ATT and ATU are observable because the only one of the potential outcomes is realized. For the treaty, the assignment Ti is 1, and the potential outcome for the treated case Y1I is observed, and the other potential outcome Y0I cannot be observed. For the untreated, Ti is 0, and the observation is reversed. So the potential outcome for the untreated case Y0I is observed, and the other potential outcome, y1i, cannot be observed. Then, let's see what is the difference observed in the data. The observed average difference in the sample is the difference between the average outcome for the treated, which is the conditional average potential outcome for the treated case, the expectation of y1i given di equal to 1, and the average outcome of the untreated, which is the conditional average potential outcome for the untreated case, the expectation of y0i given di equal to 0. Adding and then subtracting the same does not change the result. So let's put these terms in the middle of the equation. Then the first two give us the ATT, the causal effect on the treated, and the last two are called selection bias. Why are the last two called selection bias? For example, consider hospitalization treatment for patients. Let's say D is the indicator variable for the hospitalization, and if hospitalized, D equals 1, and if not, D is 0. And let Y1 be the health condition after the hospitalization, and Y0 be the health condition without the hospitalization. In a hospital, not all patients are hospitalized, and the patients to be hospitalized are not randomly decided. In usual, critical patients whose Y0 may be lower than others are more likely to be hospitalized. That is, the average Y0 of the hospitalized patients, which is the first term of the bias, may be lower than the average Y0 of the not hospitalized patients, which is the second term of the bias, leading to a non-zero bias. This bias distinguishes the average difference observed in data from the ATT, the theoretical causal effect, and comes from the non-random selection of patients to be hospitalized. And that's why the last two terms are called selection bias. In reality, the selection is non-random, leading to a non-zero selection bias. But this is unfavorable for causal inference. For causal inference, the selection bias should be 0 to identify the causal effect by the average difference observed in data. And this problem is usually called the selection problem. And now I'm going to present one ideal condition that makes the selection bias 0. It is called independence assumption. The independence assumption means the treatment assignment D is independent of the potential outcomes Y1 and Y0. In other words, the independence assumption implies the treatment assignment is randomized. If that's the case, the conditional expectation of the potential outcome is the same regardless of the assignment, the value D, and it becomes the same as the unconditional expectation of the potential outcome. Under the independence assumption, the average difference observed in data becomes the unbiased estimate of the theoretical causal effect. The average difference observed is given by the sum of the ATT and the selection bias. But the selection bias becomes 0 because of the independence assumption. So only the ATT remains, and it becomes the same as the ATE, the unconditional causal effect, because of the independence assumption. For better understanding, let me give you a simple example. Consider a surgery treatment on cancer patients. There are 10 patients who have cancer, and they received one of two treatments, a surgery and a chemo. The I indicates the treatment assignment. If the surgery received, the I is 1, and if not, the I becomes 0. Then suppose that we focus on the post-treatment lifespan as the outcomes. Furthermore, suppose that we know the potential outcomes, that is, we exactly know what would happen if each patient received the other treatment. And suppose that the doctor who decided the treatment didn't know the potential outcomes, but she is super talented, so perfectly assigned each patient to the best treatment. That means the independence assumption is violated. This is the table of the outcomes. The second, third, and fourth columns present the potential outcomes and the difference for the patient. And they are unobservable in reality. And the fifth column shows the selection, indicating which treatment each patient received. And the last column presents the observed outcome. It is the same as Y1 for the surgery treated and Y0 for the chemo treated. Because we know the potential outcomes as in the table, we can compute the theoretical causal effect. The ATE, which is given by the average of delta across all of the patients, is 0.6. Because the assignment was not random, the average difference observed is different from the ATE. Those patients shaded in orange are the patients who received the surgery treatment, and the unshaded patients are those who did not receive the surgery treatment. So the difference in the average of Y between the shaded and the unshaded is the average difference observed, which is minus 0.4. This number is different from the ATE, and the observed difference is also different from the ATT. The ATT is given by the average of delta only for the surgery treated, which is 4.4. And the selection bias is given by the difference in the average Y0 between the surgery treated and the chemo treated, which is minus 4.8, confirming that the average difference observed in data is the sum of the ATT and the selection bias. Now, make a little change. Suppose that we still know the potential outcomes, but now the doctor who decided the treatment was a fake doctor, and she just randomly assigned the patients. That is, the independence assumption holds. This little change makes a huge difference. The ATE is still 0.6 because it is unconditional on the assignment. But all of the others change it. The observed average difference is now minus 0.2, which is the same as the ATT, and the selection bias is now 0. And here, I strongly recommend you to pause the video and manually compute the values by yourselves for your better understanding. So far, the data we mainly discuss in this course on macro marketing data, though, I have introduced the potential outcomes causal model that looks like focusing on individual person in an experiment. Why? Let me go back to our discussion for the proper variation for the price discount problem. Treatment group and control group are necessary to infer the increase in sales caused by a price discount to decide whether to discount the price. And suppose that we found sales increases during the discount. That is, the period with the discounted price serves as the treatment period, and the other period becomes the control period. And it is implicitly assumed that the distribution of shoppers is identical across the periods, implying that there is no selection bias. That is, the full causality is still valid even with macro marketing data. In the medical experiment example, the unit of analysis is an individual patient. In micro marketing data, the unit of analysis becomes an individual consumer. In macro marketing data, the unit of analysis is time, market, country, and so on. But even with macro marketing data, the independence assumption must hold across all units in analysis, as in the price discount problem, in order to accurately infer the causal effect. The independence assumption enables us to have the unbiased estimate of the causal effect for experiments, though, but it is still not enough for marketing data in general, because most marketing data are observational data. Data generating mechanisms are real life, which is far from well-controlled experiments. In that, there can be so many other factors that potentially influence the causal effect of a marketing action. So, we need another device to separate out the causal effect from the potential confounding factors. For example, consider the beer sales we discussed. Beer sales may be affected by prices and seasonality, and in the marketing data, both factors sometimes appear at the same time. Then, how to make the independence assumption still hold in such marketing data with confounders? We already have a solution, the control variables. By adding the control variables for the confounders, we can make the independence assumption hold. To show that the control variables work well, I first extend the independence assumption to some other variable. It is called conditional independence assumption, for short CIA, which is the generalized version of the independence assumption. Suppose that there is a confounder, X, and its level is observed. If the assignment is independent of the potential outcomes, given the level of the confounder, the assignment is conditionally independent. This implies the assignment is randomized within each subpopulation defined by the confounders. Let me go back to the surgery treatment example. In general, efficacy of a treatment depends on patient age, implying that age is a potential confounder of the treatment effect. In such cases, researchers usually conduct a separate randomized experiment for each age group. That is, the patients are divided into subgroups by age, and in each group, the patients are randomly assigned. If the CIA holds, then the expectation of the potential outcome, conditional on the confounder, and the assignment is the same regardless of the value of the assignment. And it is the same as the expectation, conditional only on the confound. But the CIA is not enough. we need one more condition, which is called overlap. This condition implies in each subgroup defined by the confounders, both treated and untreated cases must exist for sure. For example, go back to the surgery treatment example again. We now have a confounder of the treatment effect, A. And the overlap condition implies both surgery cases and chemo-only cases must exist in each age group. If both CIA and overlap condition hold, we say the assignment is strongly ignorable or unconfounded. Then, for each subsample defined by the confounders, the selection bias becomes zero in the same manner, and the average difference in the subsample becomes the unbiased estimate of the theoretical causal effect conditional on the confounders. And then, by the law of iterated expectation, the average difference over the entire sample becomes the unbiased estimate of the ATE, the causal effect unconditional on both the assignment and the confounders. Now I'm finally ready to justify the inclusion of control variables. First, consider a linear regression of the outcome y on the treatment d and the confounder x. And all of the basic assumptions for the regression are assumed to hold. Then, the regression equation can be given by y is equal to alpha plus delta times d plus beta times x plus an error, and the error is independent of d. Now, let's compute the average difference observed in the data conditional on the confounder. Given x, the average outcome for the treated is alpha plus delta plus beta x plus the conditional expectation of the error, because d is 1 for the treated, and the average outcome for the untreated is the same, but there isn't delta because d is 0 for the untreated. Because the error is independent of the assignment, the two conditional expectations of the error are the same and cancelled out. And all the other common terms are cancelled out as well. The average difference observed becomes just delta, which is the same as the causal effect of the treatment. That is, if all potential confounders are well controlled in the regression, the estimate of the coefficient associated with the assignment is the unbiased estimate of the causal effect. Then, what does well controlled in the regression mean? It means, first, all potential confounders should be observed in data. Second, all possible levels of each confounder should be observed. Third, both treated and untreated cases must be present for all of the subgroups defined by the confounders, which is the overlap condition. And last, the assignment should be randomized within each subgroup, which is the CIA. Now, let me wrap up with the Mr. Mistake and Ms. Perfect example. In Mr. Mistake's regression, the brand effect is missing and a positive relationship between the sales and price was found. We already have discussed that the missing factor, the brand effect, confounds the effect of the price. And let's assess his regression with the potential outcomes causal order. First, price, which is the treatment, is not randomized for each brand, which is the subgroup defined by the confounder. This is the violation of the CIA. And second, for brand C, there is no high price case at all, which is the violation of the overlap condition. Thus, the difference in the average quantity is biased. On the contrary, Mies Perfect added the brand dummies into the regression. With the dummies, the price is now well randomized for all brands, implying that the CIA holds, and both low and high prices are observed for all brands, indicating that the overlap condition also holds. So, the difference in the average quantity is now unbiased. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, an online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.